Hello, executive team. Thank you for joining me today. We are here to discuss a strategic initiative that strikes at the core of ABC Bank's growth and operational efficiency, the modernization of our credit card approval process. So, for over a century, ABC Bank has built a legacy of trust. However, our current manual review process for credit cards is time-consuming, expensive, and susceptible to human inconsistencies. Today, I am excited to present our new machine learning solution. This model will not only automate and streamline approvals to improve customer experience and reduce operational costs, but it is built fundamentally on the principles of responsible AI. So I will talk you through our methodology, how we ensure fairness and compliance, and how we retain full transparency in every automated decision we make. So first of all, data foundation and preparation. So let's begin with our foundation, the data. As our chief data officer knows, a model is only as good as the data feeding it. We started with a comprehensive exploratory data analysis of our historical application records. We found that our data was highly imbalanced. About 87% of historical applications were rejected, and only 13% were approved. So if we fed this directly into a standard algorithm, the model would simply learn to reject everyone, which obviously does not serve our business goals. So to prepare this data, we performed a rigorous pre-processing. We scaled financial figures like income, encoded categorical features like housing and education, and most importantly, we applied a technique called SMOT. This algorithm safely generated synthetic examples of approved applications, balancing our training data so the model could learn the characteristics of a good applicant just as well as a risky one. So in the code, you can see here our EDA process. And here are some graphs showing the distribution of several variables and the correlation matrix. And next part is about the data um, preparation and pre-processing here in the code. And also you can see the training set and we develop. Okay, so the next part is about the model selection and strategic metrics. We had to choose the right engine for the job anyway, so our model selection procedure was rigorous. We tested three industry standard algorithms, logistic regression, random forest, and XGBoost. To evaluate them, we didn't just look at accuracy. In banking, predicting a default is entirely different from predicting an approval. We focused on metrics that represent real financial risk, precision, recall, and the LLC AUC score. So for instance, recall helps us understand how many genuinely good applicants we might accidentally reject, while precision tells us the reliability of an approval. Through fivefold cross-validation, the random forest model emerged as our winner. It achieved an impressive ROC-AUC score during training, meaning it is highly capable of distinguishing between risky and sane profiles and safe profiles. So here is our code for the model selection, and you can see the random forest ROC-AUC score is the highest. And next up is about the model valuation and learning curves. So of course, the chief risk officer will ask, how do we know this model will work in the real world on data it has never seen? To answer this, we assess the model's fit using learning curves. So a learning curve plots the model's performance as it learns from more and more data. What we observed as a tight convergence between the training performance and the cross-validation performance. So this is the exact signature we look for to ensure the model is not overfitting, meaning it has not just memorized historical data, and it is not underfitting, meaning it has successfully captured the underlying financial patterns. And while our initial test set evaluation showed conservative approval rates due to the raw data's massive imbalance, the underlying architecture is sound and highly tunable to our exact risk appetite. So here you can see the code of model training and evaluation as well, the random forest test performance, and the confusion matrix, and also about the learning curves we built. Okay, so next part about the responsible AI. Now I want to address a critical question, particularly for our chef compliance officers. So how did we ensure our model adheres to responsible AI principles, and what steps did we take to evaluate and mitigate fairness or bias concerns? So at ABC Bank, we cannot deploy a black box that makes discriminatory decisions. To ensure our model adheres to responsible AI principles, we proactively tested it against sensitive demographic groups in our dataset, specifically focusing on gender. We calculated two critical industry standard fairness metrics, the demographic parity difference and the disparate impact ratio. The results were excellent. The automated approval rates between different genders were nearly identical, sitting at roughly 6.2% for both groups. Our demographic parity difference was 0.0001, so which is essentially zero, and our disparate impact ratio was virtually one. So for our chef compliance officer and our legal teams, this is the exact empirical evidence needed to prove the model does not exhibit gender bias. To proactively mitigate future bias concerns, our machine learning pipeline is designed so that sensitive demographic attributes are strictly audited. By continuously monitoring these fairness metrics in production, we ensure that as the data changes over time, our model remains strictly compliant with fair lending laws, such as the ECOA, effectively shielding the bank from legal and reputational risk. So here you can see the code for responsible AI and the fairness metric. Okay, so next part. So to improve this, this brings us to the second critical question, basically regarding responsible AI. So what techniques did we implement to improve the model interpretability? And how do these techniques support responsible decision making? So in financial services, we can never simply tell a regulator or a customer, the algorithm said no. We must be able to explain exactly why. To achieve this, we implemented SHAP, Shapley additive explanations, which is an advanced mathematically proven technique used to decode complex machine learning models. We implemented SHAP at two distinct levels, global and local. So globally, SHAP provided us with a macro level view of what drives the model's logic overall. It confirmed that account length, age, and total income are the most significant factors driving credit card approvals. So this is highly reassuring for our risk team because it proves the algorithm is learning sound, logical financial principles rather than arbitrary or risky patterns. And locally, SHAP is even more powerful. It allows us to generate a specific individualized breakdown for every single application. If a customer is denied credit, the SHAP waterfall plot shows us exactly which specific factors pulled their score down. And for instance, perhaps their account history with us was too short. So this logicalized explainability is transformative for responsible decision making. It enables our customer service teams to provide clear, actionable, and transparent feedback to the applicant. And furthermore, it ensures we can effortlessly generate the accurate adverse action notices required by financial regulators, entirely removing the black box stigma from our AI adoption. And here you can see from the code, the SHAP feature importance graph, and also the summary plot, and finally the explainability for a single prediction here. So finally, in conclusion, we have built a robust, highly capable machine learning pipeline. It stands ready to modernize ABC Bank's credit card operations. By adopting this data-driven approach, we expect to see a drastic reduction in manual review times. This directly translates to lowered operational costs and a significantly improved customer experience through near instant decisions. Most importantly, we have achieved this without compromising our century-old legacy of trust. Through rigorous fairness testing and sharp explainability, we have mitigated the compliance and reputational risks typically associated with AI. We are not just innovating, we are innovating responsibly. So our next steps involve fine-tuning the model's exact approval thresholds to perfectly align with the board's current risk appetite, followed by a phased shadow deployment where the model will run alongside our current human analysts to validate its real-world performance before going fully live. And here is the final part of my code. So that's it, and thank you for listening.